Thank you, everyone, for coming. My name is Anthony Lineberry. This is David Richardson and Tim Wyatt. We're researchers at Lookout. We do a lot of cool stuff with mobile security. So today we're going to be discussing permissions on Android and some of the fun things that we can do with and without some of those permissions. So to get started, things we're going to cover, we're going to do a brief overview on the Android internals, just to get those of you who don't have any context about the important components within Android and a lot of the things that we're going to be discussing, as well as the security and permission model, basically just how their sandbox works, their permissioning, how that's implemented. But then we're going to discuss some of the fun things that we can do with the permissions. Basically things that we can do without permissions, things that we can do with permissions to do things that that permission didn't intend for us to do. Also, we're going to discuss system logging and how we can leverage that to perform a lot of these actions as well. After that, we'll discuss routing and a lot of the problems surrounding that and everyone's quest for root on these phones. And then we'll discuss some mitigation, basically things that we would like to see people do, the end user, see developers do, manufacturers and OEMs. So let's get started. The Android internals. So the first thing we have is our Android manifest. It's something that every application has. This is a large XML file. It's stored as binary XML because things need to be small and mobile. The manifest contains everything important about the application. Primarily, it's going to contain the package name, which is a unique identifier for every application. Essentially, this is when you see like com.android.sms or something like that. Those are the package names. These also are going to describe all of the components of the application. So all of your activities, all of your intents, broadcast receivers, that kind of stuff. Also, all the permissions that the application needs. So it's going to declare both requested permissions that the application needs to access a lot of the protected APIs and a lot of the content, as well as declare permissions for that other applications would need to access components within the application itself if they want access to some of the activities or to be able to receive intents and the application has set permissions to access that. So yeah, activities. Activities on Android are basically just a UI screen. This is a way for a user to interact with an application. The activity itself is going to be composed of views, which on Android are essentially just your UI widgets, your buttons, image views, text views, a lot of things like that. The activities themselves are managed in an activity stack. So essentially, any new activity that is created or started will be running in the foreground on top of the stack. This will be in an active state. Any older activities or before that are going to be lower down on the stack. Any activity further down on the stack will also be in a pause state where it just maintains state of the activity itself. The activities will stay in this activity stack until the activity itself finishes, or in scenarios where the system memory is low, if an activity is paused, then it can be killed by the system itself. Activities can be started by other applications. So an application itself can start a remote activity in another application. So a scenario for this where someone might realistically do this, a lot of applications will request a location permission. That location, if they want access to fine-grained location data as far as latitude and longitude, they have to have their GPS enabled. So an application can start an activity to fire up the settings for the location that are actually built into Android, pull that activity up, and then the user can check the box to enable GPS. Once the application sees that that setting is enabled, then they can finish that activity and be brought back to the original activity that they were at. The activities themselves, when you start these activities within another application, run within their own application's process. So if you're starting some other application's activity, you won't necessarily have access to any of that application's data or any of the activities data. But starting activities within your own application, of course, you'll still have access to a lot of the data associated with that. Activities, like we said earlier, you can define in the manifest. If you don't want people to be able to start your activity, you can request a permission to be able to enforce access to this, that any application that wants to start your activity would need to request this permission and be granted that to start it. Intents. So Android intents are basically, in the documentation, it says an abstract description of an operation to be performed. So this is essentially just a simple data structure of an action and data associated with that that's passed in the form of URI. And we use this as basically low overhead IPC between applications so that we can say, hey, we want to start a browser, here's a URI for this, or we want an action view, here's some content data. We can use the intents to start, or as we said, okay, so we use these to start an activity. We can also use these to broadcast system-wide an intent with send broadcast. So in an event where we receive an SMS, or an SMS is received on the platform, an intent will be broadcast out to everyone, to pretty much anyone who sets up a listener can receive that intent if they're interested. We can also use these to communicate with the background service. So if we have a service set up in the background, then we can send intents to that along with data to notify it about certain events, and that kind of stuff. Broadcast receivers. So this is the receiving end of an intent. When you send these out, an application will have a broadcast receiver set up with some kind of intent filter of the intents that they want to receive. So if you want to be notified about an SMS being received, you'll receive an intent usually containing the SMS PDUs, I believe. So we can create these in two different ways. We can either create a broadcast receiver dynamically in our code with registered broadcast, or statically within the manifest using the receiver tag, and we can define that. And we can receive two types of broadcasts, two types of broadcasts with our receiver. So we have a regular broadcast, which is just sent out asynchronously en masse to every receiver on the system. These types of broadcasts cannot be aborted, and you can't do anything with the result. We also have an ordered broadcast. This is a broadcast that's sent out sequentially to all the receivers. So as it goes down the line, a receiver they'll receive the result from the previous receiver and do any kind of processing they want on that. They have the option to abort that broadcast, and from that point it won't go any further down the line to any of the other receivers. And also we can pass our own result to the next receiver down the line. Much like the intents and activities, we can enforce permissions from both sides of either the sender saying, this is the permission that you need to have if you want to receive this broadcast, or if the receiver is going to receive it. The receiver can also say, this is a permission you need to have if you want to send me an intent. Services are basically what they sound like. It's a component that we'll use in the background to do processing. These are not a separate thread or a separate process. The services themselves run within the main thread of the application. So if you want to do any kind of CPU intensive processing or anything that's going to do some blocking, you're going to want to spin off your own threads to do that kind of stuff. But essentially, we can use these much like an activity. And we can also enforce permissions like the activities and intents before, where you define a permission to say, if you want to access this service and use it, you need to have this permission. So let's talk about the security and permission model of Android. So everyone knows that Android is using a sandbox. It's one of the highlights that everyone likes to talk about. The sandbox itself is not a VM. A lot of people assume that the sandbox is basically the Dalvik VM that's running, but the sandbox is actually just users on a Unix system with UIDs and GIDs. So essentially, every application that you install in the system is going to run as a different user. So applications, in that sense, won't have permissions to access other applications, files, and data on the file system. And every process is running as a separate UID. So all those processes are going to have a VM, which is a lightweight. So the Dalvik VM is just a lightweight Java-like VM that's actually based off of passing registers rather than on the stack. If you find a way to break out of this VM through an attack, it's not going to gain you anything because you're still just running within that process with those users' permissions. And there's a lot of legitimate ways to break out of the VM anyway using JNI code, which is natively supported now. You can have a shared UID between applications if they request to do this in their manifest. Both applications have to request this, and essentially these two separate applications would be the same user, but both of these applications need to be signed with the same signer key. The permissions on Android essentially just act as fine-grained access on top of the sandbox to be able to access protected APIs content. So if you want to be able to access the SMSs that the user is receiving, if you want to be able to access their contents, if you want to be able to access the internet and have network communication, you're going to need to request a permission. And as I said, these are all declared within the Android manifest. So with all of that background in mind, David is going to talk about some of the fun things that we can do with these permissions.
Thank you, Anthony. So yeah, now we move on to Android development. And my motto here is, why ask for permission when you can ask for forgiveness? So why are permissions important? Permissions, they gate what an app can do, and these are actually user visible. So I pull up my phone, I access the Android market, I click on an app that I want to download, and I see a screen like this. So this is Pandora, and I see that it can access the internet, it can read my phone state, and do other various things. Now, as a user, I'm required to okay this before I can download or install an application. There's no you can't agree to allow an app to do some things, but not others. It's all or nothing. If you don't want to allow these permissions, you click cancel, you can't install the application. And so users can look at this screen and they can decipher to some degree whether or not this makes sense for the application. So it's Pandora Radio, obviously it needs to be able to access the internet. It wants to be able to read my phone state because it doesn't want to keep playing music if I receive a phone call, for example. So let's look at another example. Here are two different tic-tac-toe apps in the market. So we can see the one on the right here requests access to the internet. Maybe it has a high score, maybe it has multiplayer or something like that, and it can view the network state. The permissions at the bottom are ones that are deemed less dangerous. And so that makes sense for that app. And then there's another tic-tac-toe app that's popular in the market that asks for similar things, but it also asks for system tools, mount and unmount file systems. So a user can see something like that and decide that doesn't sound right for tic-tac-toe. So that's sort of why permissions matter. And what happens if you request 0 permissions? This Solitaire app requests 0 permissions, so when I click install, it just starts downloading it. And so why should a user be worried about an app that requests no permissions? If the OS isn't going to warn me about it, I should just assume it's safe, right? Well, I'm going to show you that that's not the case. I'm going to go through and explain what exactly you can do with only 0 permissions. So the first thing you can do is you can actually reboot a phone. There's a reboot permission, and this permission is set as protection level signature or system. And what that means is that you have to either be on the system partition or you have to be signed by the same signature as by the manufacturer of the phone's signature, and therefore most apps can't access this. There's no way to be installed from the market onto the system partition, for example, unless you were already there. But that's not going to stop us. So there's a couple different approaches here. One of them that we found that's sort of the easiest and most reliable involves toast notifications. So a toast notification is a notification of something that occurs in the background that will appear on top of any activity that you're running. You can think of this as like a growl notification. So here's an example. Someone's in the keypad application and a toast notification pops up and tells them something about something that happened in the background. So here's just a simple, this is kind of the hello world of creating a toast. You can just easily call this helper method and display a toast on the screen, and then all I've done is throw it inside an infinite loop. And every time that you create a toast, it actually creates a weak JNI reference in the system server. And as you can see, at 2001 global references, the system says, "I can't let you do that, Dave," and crashes with a SIGSAG V. So the actual version kind of or the actual number of references sort of depends on the phone, but we found 2001 is almost every phone at 2001 global references. System server crashes and the phone reboots. All in all, that process takes about 20 seconds from when you display the first toast. So any app with no permissions can cause a phone to reboot within about 20 seconds of launching. But that would actually display the text "Hello World" on the screen for 20 seconds before your phone rebooted, and you might notice that something was up. So we can actually do something that's called a custom toast. So we don't have to just display text. We can actually display any view that we want. So here's an example of Powdered Toast Man, an image of Powdered Toast Man being displayed on top of the phone screen as our custom toast. But we can also create a custom toast that is completely invisible. So here, this code snippet just shows creating a new view with nothing in it and then showing that. So this is completely invisible. The user has no idea that anything's going on except maybe that their phone is heating up a bit, and then in 20 seconds their phone will just reboot. So now that a phone is rebooting, we might want to request the receive boot complete permission. So this permission allows apps to automatically start on boot. And this one's just a little too easy. You can just comment out the request for the permission. It still works. It works on all Android OS versions. This permission is not enforced, period. And in fact, if you do the previous attack, the 20 seconds that it takes to reboot the phone again actually starts much earlier than when the user can interact with it. So, if you combine these, you'd maybe have a few seconds before your phone just reboots again. So another thing that a lot of app developers would like to be able to do, and malicious developers as well, is to be able to start an app on installation. So you can imagine that you could combine this with say, a phishing attack. You download an application and you're in the Android market and a pop-up appears as soon as you're done downloading it. You don't suspect that it has anything to do with the application that you just downloaded it, because apps can't run until you start them. That's like a principle of Android. So if you could pop up a screen that said, "Please enter your Google username and password," you might actually believe it. So there's no permission that allows this functionality, but there is still a way to do it without any permissions. The Google Analytics has a referrer tracking, and this code snippet is actually just stolen from the Google Analytics SDK for Android apps. And basically what it does is it allows you to track the source of where someone downloaded your app. So maybe they clicked on an AdMob link and you want to be able to see which AdMob link they clicked on, or maybe they clicked from a website and you want to be able to see what website linked into the market to your application. But we don't have to use the Google Analytics receiver here. We can just write our own receiver and have this exact same intent filter, and we'll be able to start as soon as an application is installed. But there are some caveats here, namely that you have to have a referrer associated with the download. So if you were just browsing through the market and you clicked on an app to install it, this wouldn't necessarily work. It would work if you clicked on an AdMob link or a web link with any sort of referrer information attached to it. However, in Android 2.2, they actually added a new feature that always includes a referrer that tells you, in this case, it tells me that I downloaded this app from the games category in the free section, and it was the 34th item on the list. So as of Android 2.2, you can expect this to work on every single download of your application. So the next thing that I want to talk about is what we call the circle of death. And this is basically a hostile takeover of the UI without requesting any permission. So this is something that, once again, any app on your phone can do this. Any app that you download, Solitaire, Tic-Tac-Toe, etc. What you do is you just launch an activity that consumes all key presses. So here we've just overridden the on key down event and just returned true, which says, oh, we handled that key press, don't pass it on to anyone else. And there's a caveat there, though, that you can't actually swallow the home button. So the home button would still allow someone to get back to the home screen. So what you need to do there is just relaunch your activity when it exits. Of course, Android doesn't make it that easy. You can't just, as your app is exiting, launch the intent to start your app again. They do detect that kind of behavior and stop it. So that's where the circle of death comes into play. So when the activity is destroyed, all you have to do is launch a service. And so here we launch a restart service in our malicious activity when it's destroyed. And all that service does is relaunch the original activity. So it's just a cycle, and then as soon as that app dies again, the service would start again, launch the activity again, and you wouldn't be able to escape from this without, say, restarting your phone, or you can actually reboot into safe mode, which makes it so no non-system apps are running on your phone, and then you could find the malicious app and uninstall it. And if you want some bonus points, you can do something fun like play a nice sound. So here I have an example of an application that would just completely take over the UI, and you could pay $5 on PayPal to unlock it. You could donate to someone. If I hit any buttons here, nothing works. And so I'm just going to pop out the battery. Once again, that's something any app can do, no permissions requested. So the last thing I want to talk about is exfiltration. Can an app that is not requesting the internet permission access the internet? If an app doesn't request internet, someone might be more willing to trust it with other permissions. Maybe I'm not worried about an app that can read my contact data, as long as I know it can't send it off to a server. And I would be willing to install that app on my phone if I don't see this permission. But if I see both of those, I can assume they might be stealing my contacts. So your app's sandbox can access the internet, but that doesn't mean that it can't communicate with other apps. So an app can simply ask its neighbor, which their activity will run in their own sandbox. So the simplest way to do this would be to just pop open a browser. So we can just pop open a browser and point it at a URL that contains some information about, say, the user's latitude and longitude, and sends that off to a server. However, that does actually pop open a browser. You can't pop an activity to the bottom of the stack or anything like that. It forces, anytime you start a new activity, it's on the top of the stack. So the user would see this, and that would kind of give away what you were doing, but at least you would have gotten a message sent out to your server. However, I'm willing to bet that we can actually do this secretly. So, of course, the easiest thing to try would be to just obscure the browser. Create another activity right on top of it, right after you create it, and hope that the user doesn't see anything. Unfortunately, this actually does stop the page from loading. So let's try something else. Let's try only popping open the browser if the screen is off. So we can actually detect our APIs to tell if the screen is on or off, and we could only do this while the phone was in the user's pocket, for example. So all we need to do is make sure that when the screen turns back on, we close the browser, and it would also be useful to redirect to a safe-looking URL. So if the user pops open their browser later, they're not like on some weird suspicious page. Or if you want to do even better than that, you could try to read the page that the user was on recently from the logs, which Tim will be discussing in detail later. So here's the basic code for what you would do. You just ask the power manager, is the screen on? If the screen is on, or if the screen is not on, then you would pop open a browser, and if the screen was off, you would, and a browser was displayed, in that case, you would just launch the home intent, which is the equivalent of pushing the home button, hides the browser, and you don't see it anymore. All that, 0 permissions. If you wanted to kill the browser, it would require permission to kill another task, and that might look suspicious. But this is a way you can do all of this with 0 permissions. So that gives us one-way communication. But what about two-way communication? Can we also receive a message back from the server? And yes, of course we can. So an easy way to do this would be to just pop the browser open to, say, a zip file, anything with a downloadable content type, and the browser will automatically save it to the SD card in the downloads directory, and anyone can read that. You don't need any permissions to read any file off of the SD card. However, there are some downsides to this. So it actually builds up a notification every time you download a file this way. And so you can see it would just create hundreds and hundreds of notifications for the user, and they would probably suspect that something was up, but you would have succeeded in your goal of two-way communication. If you want to clean up the file system afterwards, you'd need the right external storage permission. However, I will point out that this permission is actually automatically requested for every app that wants to support Android 1.5. Therefore, people are very used to seeing this permission. So how about we try something else? How about a custom URI? So we can register, or Google Maps registers for the protocol geo, like latitude, longitude. And when you click on a link of that format, it automatically pops up the Google Maps application and shows you that location. So we can actually do the same thing with our application. We can register ourselves for the NetHack protocol, and then the page on the server side can automatically redirect to a page like NetHack data with some private information that would be the response from the server. So here you can see this is a statically declared activity with an intent filter inside our Android manifest. We're requesting the NetHack scheme, and the host is data, which is just what should be the first section of the what's the host of the URL. So you can think another example here would be the YouTube app would set the scheme to be HTTP, and the host would be youtube.com, and that's why when you click on a link to a YouTube video, it opens in the YouTube app instead of in the web browser. And note that this is actually an activity, although we're using it like a receiver. So this would be something that we would want to happen completely in the background with no user interaction at all. But the idea behind a data intent filter is for something that does involve user interaction. This is supposed to be, I click on a link in the browser, I click on a telephone number in the browser, I click on a map location, something like that. It's supposed to pop up an activity. So here's the activity that it would pop up. In this case, after that page on the server redirects, it would go to, it would launch this activity with an intent that contains the data that we set on the server. So here we've set a parameter in after we redirect, and then we can just log the intent, and it has the data that we're looking for in that intent. And we call finish in the onCreate event here, and we never display any UI. This happens instantaneously. Nothing is seen by the user when something like this happens. Again, the same caveat that I pointed out before, you probably want to send the user off to another page so when they open their browser, they don't see anything funky. So now what I would like to show you is it working in action. So there's two things. On the top here, this is my Apache server logs. So we can see the last thing was about an hour ago, the last hit that we got on the server. And at the bottom here is actually the logcat output on this phone here. So you can see the screen is on, and if I turn the screen off, after about 5 seconds, we should see, so it's starting an activity here, we can see that. And then up here, we should see, hopefully, yes, there we go. So here we have every 5 seconds, it's going to ping back and forth between the device and the server, and can send any information back and forth along with this. This is an app that's requesting no permissions. If I turn the screen on, you don't see anything on the screen. It's still just the home screen. Stop sending data immediately, and then turn the screen back off. And starting the intent down here. And there we go, the Apache logs. Thank you everybody next door for cheering for me. Yes. So now that I've showed you all the cool things you can do with zero permissions, Tim is going to show you a bunch of awesome stuff you can do with only one permission.
So here's a pretty typical example of how a typical application actually, would write debug data to the system logs. We import the Android util log class. We declare a tag that will prefix the log entries when they go into the system debug log, and we use a relatively simple API to leave traces there. You'll see lots of examples of these and heavy use of it in a lot of code. So on the Android image, there are, well, up until 2.1, there are three different log devices that are actually available. As of Froyo, we've seen the appearance of a fourth log. It's not entirely clear what the split is there yet, but it is available. Devlog events is described in the reference documentation as not the main logcat debugging facility. These are diagnostic events for system integration or system integrators and not application authors. For the most part, there's nothing interesting there, but we'll see something developers should be aware of in a minute. Devlog radio contains the log output stream for the system radio. Typically, this includes a lot of command stream gibberish that most people don't want to pay any attention to, but there are some interesting events that pop up in there as well. And then devlog main is actually, as I said, it's the main application log. When your typical market downloaded application uses the log facility, this is actually where the output ends up. So the logcat utility can be used to look at these logs. Typically a phone that's got debugging enabled, you'll just use ADB to look at that when you're working on your app. Now, ability to read logs is gated by the read logs permission. So this is not as fun as some of the zero permission stuff that David was talking about, but it's still kind of interesting. In the case of a phone that's in debug mode, the shell account is granted permission so that you can invoke logcat over ADB. And you can kind of look at read logs as a permission, which, in some sense, to uneducated user seems like a relatively harmless thing to request access to, but it can actually be built on. There's advice in the permission documentation that logs may contain some private information, but should never contain serious private user information. So in order to explore some of the things that might be hanging around out there, we put together a client. It's a relatively simple Android service. It asks for read logs. As implemented, it does ask for internet, although you can imagine putting this together with the NetHack approach that we can probably work around that. It downloads some policies from the server and applies essentially a set of regexes to the logs, extracts some stuff, and sends it back for analysis. So high level, we have a logcat device, which in this case is just a relatively simple wrapper around the logcat utility invoked from within an application. We're going to open that device and we're going to set up a line-oriented reader for it. We have a log monitor, which is actually responsible for kind of the primary data processing thread here. We'll pull each log of line output out. We'll match it against a set of filter criteria that we've established. And if something looks interesting, then we'll actually track it for delivery to the server component. And this is written as a service. The service fires up, attaches logcat devices to all of the available logs on the device, and requests start sticky so that we actually run in the background. So when the activity attached to the service is not available, it'll still be processing output. So there's also a server component here. It's a relatively straightforward set of Rails components. It's essentially responsible for command and control, policy delivery, and processing the data delivered by device. So we're supplying per device policies to devices connecting back. We're receiving logs that meet those policies that the device actually delivers. We've got an interface to explore the output, go through and see what it is that was actually sent out, and some facilities for post-processing specific log data that we're interested in. A little bit about the policies and the approach that we took here. We started out with a set of random keywords, just a few ideas about things that might be going on in the system. We threw in there insert, update, delete. These are things that are going to appear in SQL statements interacting with data providers. We threw out intents. Intents are obviously a pretty core mechanism for triggering interaction across applications and IPC. Content, looking for anything that might be related to content providers. HTTP, looking for things, protocols. You can imagine, a number of things that go on past there. We also picked a couple of interesting, pieces of data to toss around. There's a keyword in there for first name, for last name, pre-picked phone number, things that might get dropped into the UI that we can flush through services and see where things come out. Set up a set of initial expressions, started pushing data through various interfaces, and looking for places that it came out that maybe weren't anticipated. So one of the first things that we noticed, as I mentioned before, in the event log, there's actually something that pops up on Froyo that we hadn't seen before. This appears to me to actually be old code that's typically been disabled, but is actually enabled on Froyo images that have popped up. And there's a hook in the SQLite database driver to actually sample sets of queries based on the runtime performance of those queries. It only logs the first 64 characters of the query, so you're not gonna see the whole thing in here. But it is something the developers should be aware of if you're concatenating statements together, and those statements contain data. They could make their way to places that you didn't actually intend and have no control over. Similarly, there seems to be a similar hook in there for content providers. And here's a case where we actually see a query that was triggered that includes phone number data. Nothing earth-shattering here, but it is worth taking note of and being aware of as a developer. So as I said before, read logs can end up being kind of an alias for other permissions that are declared on the system. So there is a get tasks permission that allows you to query recently running tasks. However, as most of those things are triggered by intents, we can actually scrape that out of the logs and just keep our own state tracking there, and keep our own table of what tasks have been running. There's a dump permission that's not entirely clear what it gates, but we have an idea, and there are actually applications that are intentionally doing this. If an application is terminated by the runtime, then a lot of information about that termination may be logged to the system logs. And if you have read logs permission, you can just scrape it out of there instead of actually asking for the dump permission. There is a permission that gates reading history bookmarks, and this includes basically looking at URL history and looking at what's in the bookmark set. This is in some ways bad news for the NetHack stuff that David was talking about, because it does mean that there's a trail that you could actually see in the demo that he was doing of data that's being sent off device. But it is good news if you have a different goal, and that's to snoop on the history that's been going on here. We see at the top here kind of a core runtime intent logging that's disclosing some information about visited URLs. The browser's not terribly chatty about that. And in another case here, a chattier component that's only on some system images that actually includes full content of query string data that's attached to activities pushed through the browser. So you can see here that you could extract something embarrassing from somebody's searches. Furthermore, there are cases where we find that read logs is equivalent to having read SMS. This varies from system image to system image, but if the debug logs are turned up high enough, then you can actually see components that will log the recipient as well as the content of SMS that's sent out. And we've seen applications that are authorized SMS receivers that are turning around and then actually throwing that information right into the logs. So it also turns out that in the case of a errant application, that read logs could be equivalent to read contents or to read contacts. We have an application here that is logging the label and data content of its activity. This happens to be a contact application. You pull it up, and you'll see all of the content, all of the contact data that's being displayed on the screen thrown right into the logs for a waiting observer. One of the interesting things that we found is that read logs can actually be equivalent to having access to course location. There's an awful lot of chatter that can show up from system components. In the case of course location, we're talking about essentially resolving location data for the tower that the device is connected to. One of the first things that we found that's activated on a lot of handsets and has actually been fixed in 2.2 is logging the LAC and cell ID of GSM towers that the device is connected to. We also see the CDMA equivalent logging some latitude-longitude approximation for the towers it's connected to. We found a pretty prominent clock and weather application that's running on the home screen of a lot of devices that's logging tower data. And we also found in the radio logs there's a series of operator and tower registration events that log the MCC and the MNC of the carrier that we're connected to, and also hex versions of the cell ID and LIC. Now, the cell ID and LIC don't necessarily translate directly, but there are databases out there that we can use to resolve that to latitude and longitude of the tower that the device is talking to. So Ericsson actually has a database that can be queried remotely with HTTP, and we can take that parameter data that we scraped out of the logs, and we can turn that on the server side or potentially device side into latitude and longitude. But we can actually do better than that because, as it turns out, why settle for coarse location? Because we can actually get fine location. And again, these are things that vary from handset to handset, but we found a number of trace pieces of data that you can use here. That same clock and weather widget that I was talking about actually logs full-on GPS data on a lot of devices. There are implementations of GPS location providers that are spitting that data out, and furthermore, the underlying native libraries that tie into the GPS sets are also disclosing that. One thing to note is that these are things that typically only show up when applications are actively talking to the GPS set. Or at relatively coarse-grained intervals. So what good does that do? Well, I'll tell you a story, and you can decide for yourself. So this is a story about three guys who started out at their office in South Market in San Francisco. They had places to go, so they left the office. They walked down to the corner, and they hailed a cab. They got into the cab and started heading down 101 toward San Francisco International Airport. Pretty chatty cab driver. At some point, one of them got bored, pulled up Google Maps to see how far along they were, and we got a location snapshot. We got another one near the airport. We can see actually, showing up at the terminal. These guys boarded a flight on Virgin America, and they headed to Vegas. Landed at McCarran. We have a check-in here that's essentially at the gate. Went down, got some baggage, headed across town, and came to Caesar's Palace. Here, we actually see a lot of interesting activity, which, as it happens, corresponds pretty closely when you look at this to us checking in, going up to hang out in our room for a bit, going down to register at the speaker's desk, and then going back to work on our slides till 4 o'clock in the morning so we could actually do this talk. So now I'm going to turn it over to Anthony, and he's going to talk about something near and dear to all our hearts, which is root access to devices.
Thanks, Tim. So as hackers, we all want to strive for root on systems, and Android is no different. So we know that everyone hoped that these phones would be these amazing utopian devices that are completely open and anybody can do anything they want. But unfortunately, we know that the reality is that manufacturers and carriers are all shipping these phones locked down, so that we can't do a lot of these fun things that we'd like to. And all these people that are buying these phones, Android especially appeals to a pretty nerdy demographic. So these are the kind of people who want to kind of get down into the internals and play around with their phone. So there are entire communities that are developing around the idea of being able to root your phone so that you can mod it, put on custom images, basically do whatever you want with it. To the point where we have third-party ROMs that are available for people to install and have a lot more fun with their phones. So what are some ways that people can go about getting root on these phones? We know that Android's running on a Linux kernel. So we can take a lot of these Linux vulnerabilities that have been popping up in recent years and see if they work on the Android device. I know there have been a few in the past that people have used to be able to root some of their phones. And we can kind of just go through a lot of old databases of vulnerabilities and kind of compare them to a lot of the major releases of Android and see if any of those would apply. Here we have all the different kernel versions that each major release is using. With Gingerbread in the future, ideally released in Q4 this year, that will either be using 2.6.3.3 or 3.4, depending on whatever they decide to use. Another way is we can leverage old libraries that are shipping on these systems. So there's various imaging libraries and some other stuff that are going, they're basically shipping out the door unpatched or very old versions. You can kind of follow some of the full disclosure mailing lists and monitor some of these libraries that we know are shipping on these phones and see if any new vulnerabilities pop up on these. SUID binaries are something that most Linux systems are going to have. These have been leveraged in the past to be able to root. I believe the Evo 4G was recently rooted using vulnerable SUID binary. So, I mean, typically anything that people have been doing in the past to attack Linux are things that we can do nowadays on Android. So let's talk about something specific here. So CVE 2009-1185 was a libudev vulnerability that was reported a long time ago. It was discovered by Sebastian Kumar, and the original patch to fix this was in April of 2009, which is roughly 16 months ago. The vulnerability itself was a failed check in the netlink message. Checking the origin of the message, basically, did it come from the kernel, did it come from the user? It didn't actually care, and we could use this to, in the end result, get privilege escalation. So we took this, or actually, so recently Sebastian dredged up this old vulnerability and wrote some code to run on Android, and so you could use ADB to upload it and run it from the file system. Turns out Android was vulnerable to it on the one he tried it on. The original release was for Droid X, I believe. So we took this and we repackaged this exploit up into some code that we could trigger with JNI and packaged this up into an APK along with a payload of a connectback shell to basically be able to install this on many different phones and see who exactly was vulnerable to this. So what we found is that every flagship phone of every major US carrier to this day is vulnerable to this specific exploit. We installed this on the Evo 4G, Droid X, the Incredible, a lot of these, the new latest and greatest phones that everybody wants. So at this point, we have an APK that we can install. If we leverage that with David's launch on install, we basically have a one-shot root for all these phones. Oops. So there's kind of a problem going around these things. We know that people want to have their phones rooted. They want to be able to play with them, be able to do a lot of these modifications, have fun. So these communities that are forming, they're not looking at rooting as a security thing. They're looking at this as a way for them to accomplish these goals of unlocking their phone and being able to do a lot of these modifications. What they're not acknowledging is that all of these ways that they're finding to root these phones are security vulnerabilities that people could be leveraging that don't have these altruistic intentions. And the other problem with this is that because they want to have these methods for rooting remain, and they don't want carriers or manufacturers to patch these problems, no one wants to talk about the details of these exploits. So we'll have one person distributing a binary that says, use this to root your phone, here's the instructions to install it, but not actually disclosing any of the information about what the problem is. And so this leaves basically the majority of people that aren't phone nerds and want to do this with gaping holes in their phones that anyone could leverage if they wanted to do that. So we've discussed some of the reasons people are wanting to root their phones. So the modding phones we've discussed. Another one of the problems is the patching process is slow. Android is coming out with major releases relatively fast compared to other mobile phone platforms. But the problem is that a lot of these manufacturers and the carriers are doing a lot of their own custom modifications to extend the system and add a lot more functionality on top of Android proper. And it takes them a while to take all these changes and patch them up to the latest version. And so you have people who end up buying a 1.6 phone, and 2 months later, 2.0 or 2.1 phones are available, and they don't see an update for over a year or a year and a half to be able to use that. So if they root their phone, they can install these custom images and be able to have access to the latest releases. Also, people are going to do this just for features like tethering, things that they want to be able to do that maybe their carrier doesn't provide them, or if they want to skirt around and do this without having to pay. That's another motivation. So that's kind of wraps up the problem with all the rooting, the community surrounding that. And so let's talk about some of the things that everyone can do to kind of avoid a lot of the problems that we've talked about today. As a user, we've kind of discussed that a lack of permission does not necessarily mean that the app can't do that. If you install a game that doesn't say it's accessing content data and shipping that off to some server, that doesn't necessarily mean that it's not doing that. And you may see a lot of people that are inadvertently doing this kind of thing, not necessarily with malicious intents. And scrutinize the permissions that your app is requesting, and that's a pretty obvious one. But some of these permissions are pretty benign and seem fairly harmless. But ask yourself, like, does my permission really need to be able to read logs? Most likely it doesn't. Also, system updates, keep your phone patched, up to date. I mean, if you are concerned about if a rogue application does slip into the market, someone being able to root your phone and build up a mobile botnet, as other researchers have been demonstrating in the past, hopefully they'll stay on top of this with patches. Developers, these users, when you're requesting these permissions to access a lot of their private data, they're essentially trusting you with that. So just be aware what you're doing with that. Think about the things that you're logging. If you are logging a lot of stuff for debugging, it doesn't necessarily need to be there in production code. So, I mean, you can do a lot of the things that Tim talked about of seeding in information and seeing where that propagates out to, and see if you had anything to do with that. Also, make use of the permissions in the system. If other applications don't have any reason to be receiving your intents or starting your activities, enforce a permission so that they can't do that. Also, along the same lines with the intents, don't be sending private data that the user would care about across these intents, because all these are being logged in the system. Anyone's going to be able to see that. The OEMs, a lot of the same things that developers should be doing are the same things OEMs should be doing. They kind of should be setting the bar for a lot of these things. Because as a developer, why should you care about leaking user data if the OEM is already doing it before you did? Also, it would be nice to see better patching on some of these. Keeping up to date on a lot of these libraries, making sure that if you are using an old library, make sure you have a backported patch for that to avoid some of these problems. Same with the kernels. So yeah, that wraps everything up. So if you guys have any questions.
Most of the logging examples I saw were off HTC. Is that running with HTC Sentinel or is that just stock HTC?
So he asked if most of the things that he was that we saw being logged were off of the stock HTC Sense UI, because he noticed a lot of the logging was from HTC stuff. Some of that stuff is, and like with the clock widget, it's things that you can remove from the screen so that you're not going to be running that anymore. But not necessarily all that stuff is going to matter if it's the HTC Sense UI. Not a dime.
There's a Nexus One in my pocket. So.
How many devices would you say are starting to take advantage of secure boot loading capabilities?
I'm sorry, what was that?
Secure boot loading. A couple of devices have secure bootloaders that prevent you from loading your own ROMs.
Secure bootloaders. Can I take that one? Here's your microphone.
Yeah, so actually there are devices out there that are taking advantage of secure bootloaders, and that's actually it's actually one of the interesting things that I've seen. I think the modding community is seeing gaining root privileges on devices as a means to try to attack some of those facilities. But what we're not discussing is that secure bootloaders are kind of irrelevant. Then you still have a big security hole here where someone's obtained root access on the device.
Is that it?
On the basis that Android's effectively running a version of Linux, is SANS or anybody starting to track these vulnerabilities? Oh, and in terms of the fact that I can go out and I can see all the vulnerabilities in the normal Linux kernel listed on these sites. Is anybody actually doing that sort of thing?
Tracking the vulnerabilities in the Linux kernel?
Against the Android devices, so we can actually see vulnerability report CV.
Oh, okay. So he asked if anyone right now is currently tracking Linux vulnerabilities against Android devices. Not to my knowledge. I don't think there's any central place. I imagine that Google is probably trying to keep up on these things and tracking that, and a lot of these handset manufacturers are trying to keep up on top of these things. But yeah, there's no central location for that kind of stuff.
Hi there.
Yep.
You showed in the beginning how the normal application permissions accept model is an all or nothing. If you want to download and install the app, it's okay. These are the permissions you're going to give the app, right?
Mm-hmm.
I found it frustrating when I want to get an app and then I look at the permissions, go, I'm not going to install this.
Yeah. So
what do you foresee as the future of giving feedback to those applications and changing the dynamic a little bit so that we can say, no, you can't ask for that?
So he's asking if permissions can. So it's kind of a one-shot, all or nothing thing. If what we kind of see or where we see that going as far as more fine-grained access. So I actually just recently read a research paper of someone that. I can't remember what they call it, like Android permission extension or something like that, but they basically implemented what you're talking about of being able to grant certain permissions, like say they won't allow it to do all the things that it wants to do except access the internet. And so they built this extension in, and personally I think that would be nice to see that kind of functionality built in. But I think that they probably also see that as degrading the user experience, because if the application doesn't handle that properly, that it can't do one thing when it thinks that it can, that may be something to consider. But ideally, I would like to see something like that.
Really simple question. Where do you guys see Android security, both as attacks and as defensive applications going in the near future?
Where do we see like Android security and defensive attacks going in the future? So I mean, like the mobile world is kind of heating up a bit. It seems like it's becoming a popular topic. There are some attacks that we're seeing in the wild. It's obviously not widespread, but as powerful as a lot of these phones are becoming, and the fact that you're essentially a dedicated internet connection with all of your personal information, I do kind of see that stuff being more of a target for people that can figure out ways to monetize that. And it seems that a lot of people are doing a lot more research in this kind of thing as well.
Do you have examples of things that are outside of the application space, as far as like the attacking the browser itself, or the text messages that may come in, or things of that nature?
Like actual like proper attacks against like a specific application? We haven't really done any research into that kind of stuff. It's definitely something that we've all been talking about looking into, and seeing what kind of attacks we can do specifically against an application, and if we're able to do that, what can we do with what we gain from that. But no, that's nothing, we haven't actually looked into that kind of stuff. Okay, if that's it, then thank you guys for coming.